Dan Olds here on the 8th and final tour stop on my grand 2018 HPC Road Trip. And as they've been telling me, I've saved the best for last with Lawrence Livermore National Lab. Introduce yourself, please.
My name is Michael McCoy. I'm the program director for weapon simulation and computing at Livermore.
Tell us a little bit about the mission and the history of Livermore.
So the laboratory basically opened its doors in 1952 when decisions were made to open a second laboratory beyond Los Alamos, essentially for the two labs to essentially vet each other and fundamentally keep each other honest.
So results and things like that.
Right. So it was E.O. Lawrence, who was the father of big experiments, and Teller that were, Edward Teller were the forces behind this. And eventually when the AEC agreed to open this laboratory, even before the doors opened at this lab, Teller went off and bought a UNIVAC computer. So can you imagine in today's environment, a laboratory going off and buying a computer without years of documentation? So he just basically
signed off on it,
and the thing arrived. So this first machine, there were no compilers. It was primordial.
Completely do it yourself.
Yeah, a few thousand operations, maybe 1,000 operations per second. I can't remember exactly, but we're talking orders and orders of magnitude. Those machines might have been 10 to the third as opposed to 10 to the 17th today. Wow. Right? That's the ratio of the peaks. So the reason why they did it was we were in a period of testing, and people were interested in extrapolating away from tests as best they could. To when they wanted to do the next test, they wanted some kind of insight as to where to go and how to design. The codes were, if you want to call them codes at that time, were so primitive that they were not predictive. Right?
Okay.
They were, but they could provide insight as to the direction to go. There were 1D and 2D codes. So they were critical, and both Livermore and Los Alamos invested heavily, first in systems like UNIVAC, and then later IBM systems. Livermore had another with Sperry Rand, I think it was called the Livermore Advanced Research Computer, all through the 50s. These machines were essentially single processor. There were ideas of, for instance, with the LARC, they might have had two processors. And during this period, compilers developed, programming models developed.
Programming languages developed?
Programming languages,
Finally got operating systems down the road?
Right, and actually, Livermore and Los Alamos developed their own operating systems. Fortran was developed by a guy named Bacchus at IBM in the mid-50s. He had a team of 12 people, and one of them was lent by Sid Vernvac, was one of our guys, worked with them. And they developed Fortran. What Bacchus wanted to do was to build a compiler that would be faster than machine code. That was his jihad. That was his. He was completely focused on that. So these 12 guys worked on this. It took a while, longer than they thought. And towards the end, as Fortran 1 was about to be released, our guy, I'm sorry, I forgot his name right now, Hughes, I think was his name, said, there's so much repetitive execution in these things. Why don't we develop some kind of tool that lets us go back and re-execute as we need to? And that was called
a breakthrough.
That was called a subroutine, right? And later, and Bacchus basically said, not now. We want to beat machine code. We're going to do that, and then we'll worry about those things later.
So
and
win his war first.
Yeah, and with Fortran 2, subroutines were a feature. So it was the second version of Fortran. They did have these subroutines, but it was an interesting time. It was a time for invention, not just refinement of ideas. It was completely blank at that point, not a whiteboard, but a blackboard, right? And so it was a that's why it was such an exciting period. So that was the first phase of computing, which was serial computing. And Livermore and Los Alamos were the two big players, and there was naturally competition there, so it was with everything. Then what happened next was Cray came along. He designed the CDC machines, but then he designed his own vector machines. When that happened, that was a programming model change. It was the first revolution in programming models.
And another huge step up in performance.
A huge step up. Yeah, I don't remember now, but I mean, the serial performance of the Cray 1 was a few megaflops, and I think the vector performance was up between 80 and 100, maybe even faster. But you had to vectorize.
Yeah.
And it wasn't that hard to vectorize, but the interesting thing was that even our best codes, and this is a pretty not well understood thing, even our best codes only vectorized to about the 30% level.
Really?
Really. And I think that was probably true at Los Alamos as well. So that was the second phase. And what's interesting is when you move from one programming model to another programming model, you stop developing your physics models. What you do is you start developing alternative algorithms and rewriting your codes. It's a period, it's a stasis. There's a latency between being effective with the old model and being effective with the new model. And as we've moved through the history of computing, as we move through these phases, each transition is more taxing and more difficult in terms of code development than the previous one. So after vectors, in the mid-90s, we heard of the attack of the killer micros. That was a term developed by a guy here at Livermore, Eugene Brooks.
Oh, really?
Yeah, it was Eugene Brooks.
I've heard that before.
Yeah, it was Eugene Brooks, and
So he's talking about the DEX and the controlled datas. And
yeah,
those.
right, and
sold the new machine.
And the whole idea of taking these commodity processors that were very cheap, aggregating to get them together, finding out a way to have these communicate with each other and build a more powerful computer. So that happened just essentially as testing was ending, underground testing in Nevada.
Yeah.
And we had to move from essentially 1 and 2D codes to 3D codes because we had to use the computers much more effectively for prediction than we did in the past, simply because we could no longer do underground tests. We had enormous amount of data from the tests that we had, but which we could use to continue to calibrate our codes. But the codes had to become predictive. And as the weapons aged, they aged in non-predictable and certainly not in symmetric ways. So when in the past you could think of 2D models as being sufficient, 3D became much more important for assessments. So we had to develop 3D codes just at the time that testing ended, and that was the beginning of the ASCII program.
Yeah, ASCII
that was
red,
under
ASCII blue, ASCII white.
Yeah, and Gil Wigand and Vic Reese was running the weapons program in Washington at that time. Gil was his guy and was responsible for developing the ASCII program. It was a huge infusion of money.
I was at the Sun Microsystems Cray offshoot.
Yeah.
And I know we participated pretty heavily in that.
And so we had to start rewriting our codes. We were put on a gauntlet. I remember that the first milestone was developing 1,000 processor primary calculation. A nuclear weapon has essentially two components, a nuclear trigger called the primary and then the secondary. So we had to run on 1,000 processors. There's this thing called the burn code review. And we were put on this baton death march to get it done over a certain number of months. And then there was be a review committee, and Gil was right there, wielding the whip. And I'm telling you, it was a very exciting time, but it was enormous pressure. And people up till then, it wasn't even clear how many processors you could scale to before you would collapse under the thrall of Amdahl's law.
Yeah.
And we were talking maybe 50 processors, maybe 100, 80 maybe.
We
and
got to 64.
Yeah.
That was the biggest SMP
Right.
in the world, and that was sort of the end of big SMP.
Yeah, right.
Yeah.
So it was, at that time, MPI emerged.
Yeah.
So that was the programming model. And so that was the third era. And it lasted about 15 years. So we're madly developing codes, but at the same time, we were able to use them effectively in a period in which we could no longer test. Then what happened was in the mid-90s, people began worrying about the demise of Moore's law, but even graver was Dennard scaling, which finally died, where you reached the point where you could, as you increased the frequency and shrunk the die, you couldn't lower the voltage to keep the power dissipation constant per unit area.
No.
Which you had to do if you didn't want to melt your rack, right? So if the voltages couldn't drop,
In fact, the voltages had to increase.
Right.
Yeah.
Yeah, so the voltages got to the point where you were having transient errors and permanent errors. So that was a real problem. So Dennard died, and so the only thing that we could do was get on the back of Moore's law and add more and more transistors, and then you could only be effective as long as you could harness all those transistors, which is to exploit parallelism.
Yes.
At the same time, the memory wall was intruding itself, getting data from memory near the cores. That was becoming a problem. And the overall power consumption of these computers was becoming an issue.
And the interconnect.
Yep.
You didn't have very fast interconnects
Yes,
back then.
right. And they've improved, but they're
Yes.
still an issue.
Yes. Well, and of course, memory bandwidth.
Right, is the main one.
Yeah.
So the next thing that happened was the Exascale initiative. We tried to get that thing going several years ago, and it took many years to get funding and a coherent program together under DOE. But fundamentally, the Exascale initiative was really about navigating that programming model transition from massively parallel, what we called MPI massively parallel, to what the next thing was. And the next thing was exploiting enormous levels of parallelism using heterogeneous systems
Yes.
that employed accelerators. And the accelerator du jour is today the GPGPU. And that's the machine that we have out there, the Sierra machine.
Yeah.
And, I can say the El Capitan machine will be very similar in its architecture.
But on steroids, I imagine.
But on steroids, yeah, it will be 10x this machine and then some.
Wow.
Yeah. So I hasten to say, though, that the jump from a homogeneous system like the Sequoia system that you saw to the Sierra system is a quantum jump, right?
Yes.
Both systems use approximately the same amount of power. Sierra is 6x of Sequoia, right? For approximately the same amount of power. But the next systems after, now that we've made this transition, after Sierra and El Capitan, it's going to be tough sledding to,
From a power standpoint.
from a power standpoint and efficiencies.
What is it? You said you had 85 megawatts coming to the floor here?
Yeah, we started out at 15. We've added power over the last 10 years. We're currently at 45 megawatts.
45.
And then we're in the middle of a congressional line item that over the next 2 years will take us to 85 megawatts and I think a commensurate cooling capability. I think
Just in time for El Capitan.
18,000 tons, right. So El Capitan will be on the order of 30 megawatts.
Okay.
And then the system after El Capitan, if that comes in the mid to late 20s, that will probably be equal amount of power. So that's 60 megawatts right there. And since it takes a year to integrate a computer, you have to integrate one while you're running the old one. Otherwise, you have a lot of very angry users, right?
Of course, yeah.
So that's 60 megawatts right there, and then there's a lot of other, machinery on the floor, as you saw, clusters, storage, data, disks and whatnot. That why we're getting up to 85. So we've spent the last 4 years developing our codes, and it's a magnificent computer floor there. It's 48,000. I don't think anyone that I know of has anyone like this. 48,000 square feet, unimpeded space, 4 foot underfloor. Everything is underneath. Nothing is above the racks.
You couldn't design the space better.
What
you're trying to do with swapping computers in and out.
Mark Seeger and I basically at the highest level designed that floor 18 years ago at a whiteboard with Mark punching numbers into his
calculator watch.
Nice. Right? And I was saying 3 feet underfloor. He said, no, it's got to be at least 4. Let's see if we can get 5. And then he says, no obstructions, no pillars, no columns. He says, and he says columns are attacks on the program. Is the way he put it. So that's why it is the way it is, and that's why this building will live for as many years as it's going to live. We don't need to build a new building. All we need to do is bring in more power and cooling. We don't need to deal with structural issues. We don't need to deal with finding place to put water or whatnot. It was all thought through ahead of time.
Wow.
Yeah, so it's worked out.
That's an incredible move.
Yeah.
So the tour you got, I wonder if we could arrange for him to see the chillers that are downstairs. That is a fantastic piece of engineering in itself.
Well, introduce yourself.
So I am Brana Stesipinski. I am the Chief Technology Officer for Livermore Computing. My position is essentially that of the system architect for the center here. So I work under Michael and Terry Quinn. So it's a phenomenal story that Michael was laying out. I've been here for 20 years.
Oh, wow.
When I first arrived here, it was right as we were siting ASCII Blue Pacific. So you mentioned ASCII Red, which was at Sandia. Blue Pacific was here, and Blue Sky was at Los Alamos.
Blue Mountain.
Blue Mountain, that's it. Yeah, that's right. It was Blue Sky here.
Is there an ASCII White?
Yes.
Yes, ASCII White and ASCII Purple were here. No, ASCII White was after the blues.
Okay.
Yeah, it was 12 teraflops. It was cited after ASCII Blue here.
Who did that machine?
IBM.
IBM, okay.
Yeah, and blue was what, 3-something teraflops?
3.9.
Yeah, so 3.9 teraflops. So when I arrived here, it was shortly after the red was the first teraflop system, and then we had our first teraflop system in blue, and
Paragon, I think, was the first teraflop system.
That was the Sandia Red, and I think it was called Paragon at that time.
Yeah, that's right.
Yeah. I think it was the only one that got shipped too. Or one very small
there
I
was.
believe so.
There was some turbulence back then,
There was a bit.
but Sandia pulled it out of the fire, and they made a working machine there.
Well, they did the same thing with Roadrunner too.
No, Roadrunner was Los Alamos.
Is that Los Alamos?
Yes.
It was
They
kind of my
did.
supercomputing
They
instrument.
did Red Storm.
Okay.
Sandia did. I think it was called Red Storm.
That's right.
Right.
Yeah. So we've got.
So, but then we had White here, which was a 10 teraflop system roughly.
I think it was 12.
12, yeah. But moving up orders of magnitude, and then while I was here, I was very involved in the Blue Gene L project, which was one of the first 100 teraflop systems. And I guess it ended up being the first one with Purple right about 100 teraflops.
Yeah, Purple was just a little below 100, and Blue Gene was a low power consuming,
very highly parallel.
embedded processor type thing.
Yeah.
That was 360 teraflops. It blew the doors off the Earth simulator.
Yes, that's right. Earth Simulator was the top of the list for a long time.
Yeah.
Yeah,
and
and
so
it was like 30 teraflops.
this is a $60 million machine. The Earth Simulator was 500 million. So
Yeah.
it was, let's be fair here though. I mean, the Blue Gene L was a great molecular dynamics machine.
Yes,
It wasn't a full spectrum.
not a general use supercomputer.
Right. So,
Yeah.
truth in
General
advertising.
purpose.
Yeah.
Yeah,
But it was the beginning of the labs getting that power was going to be a problem, power consumption. It was the first advanced architecture that NNSA put down. It was actually at Livermore.
IBM wasn't sure that was even an HPC supercomputer.
It
when they
wasn't a
first developed
product.
it. They're saying, no, that's not for HPC. Why is it not for HPC? It was an analyst thing, and they're saying, well, it's not the right design. I said, well, goes fast, goes really fast.
Yeah.
Yeah, they can do everything else around
Right.
it.
So,
Well,
yeah.
so Blue Gene L was an outstanding design, but it was very difficult. It's very difficult to continue taking it further because it really depended on the fact that the chips were very low power in terms of both their capability and their power requirements.
Is that the cell broadband engine inside that? An
No,
offshoot?
no, it was. I think it was an embedded processor. I think it was from car air conditioners or something like that. Actually, yeah, and so the basic core was from an embedded system, and IBM designed a special floating point unit that went with it. And there was only just 2 cores per chip, and very low power, very much requiring you to go to very large levels of parallelism across the whole system. So it had over, so there was 96 racks at its largest of 1,024 nodes per rack, so 100,000 some
Wow.
nodes total. So one of the most highly parallel systems in terms of node count that has ever been built.
Yeah, it held, I think, #1 for something like 7 cycles.
Something like, yeah.
Yeah,
Yeah,
something
it's
like
the
that.
longest of any U.S. system.
Yeah.
I think the RAD system held it for the equivalent amount of time.
Yeah, okay, maybe, I'm not sure.
Yeah, so,
But you have, what was it, number 3, number 10, and number 11?
No, actually, we have number 2
Number 2, I'm sorry, number 2,
yeah,
number 10, and number 11.
Right.
currently. And that
Wow.
indicates something that's somewhat unique about our center. So not only do we build some of the largest systems in the world, but we have a breadth of missions that a number of people do not understand that require us to field multiple systems at the same time. So number 10 is Sequoia, which is the predecessor to Sierra, which is currently number 2. But number 11 is Lawson, which is a system that is the same architecture as Sierra, just 1/6 the size, but it serves our unclassified missions, whereas Sierra is for the stockpile stewardship
Yeah.
mission that Michael mentioned.
Gotcha.
yeah, so we actually have 2 world-class computer centers here, one classified and one unclassified.
That's incredible. There's
Yeah.
not a lot of places that have this much
Yeah.
computing power under one roof.
And the reason why we do it, the reason why we started the Unclassified Computing Center was we wanted, as the laboratory moved ahead with ASCII, we wanted the entire laboratory to move ahead. We didn't want excuse me, haves and have-nots.
Okay.
It wasn't just our being politically correct or ecumenical.
Yeah.
It was that we understood that at times that the laboratory is under pressure, we needed to be able to move people across environments and having them all speaking the same language and not a Tower of Babel of
Not
computing
silos.
equipment and right. So everyone uses the same machines at this laboratory. We treat everybody the same. They all get the benefit of our programming models and our centers of excellence and whatnot. And that's what makes this laboratory so powerful in computing.
Yes.
So our machine Sierra only has 2 GPUs per Power 9. The number one system has, at Oak Ridge, has 3 per
Yeah.
Power 9. We selected to go with 2 because we had not had any experience with GPUs. And the complexity of our codes, the multi-package nature of our codes, mediated towards having more CPUs.
Okay.
After about 3 years of hard work, we had some second thoughts.
About
Some of
changing that
our
ratio.
guys wanted to go to 3, but not all of them.
I think you could actually physically go to 4 with the NV links in there. I think there's 4 NV links per node.
Well, no. So the way it works is that each Power 9 has a set of 6 NVLink bundles.
Okay.
All right. But you wouldn't want to have fewer than 2 together because that gets you 100 gigabytes a second of bandwidth. Sierra, the bundles from the Power 9 are grouped into sets of 3, so you get 150 gigabytes a second
Okay.
per GPU. All right, which actually makes the system very effective if you're not able to fit your problem completely into the GPU memory, which, in my opinion, is something that the way you design the system indicates that you're probably, you don't want to be fitting your problem size into GPU memory, all right? Because the current GPUs only support stacks of high bandwidth memory of a total of 16 gigabytes. So we have 16 gigabytes per NVIDIA V100 or NVIDIA Volta. And so that's kind of small relative to the problem sizes that we need to run.
I
So
think they have bumped that to 32, haven't they? Their latest hardware? The Voltas?
so there was the potential to have 32 gigabytes per Volta. That wasn't going to be ready in the time frame that we were.
it wasn't ready.
And it will go up in the future. So that may change the
May change your calculus in terms of how you.
right on how you use the system. But then
That's a pretty big upgrade. I mean, it's a pretty expensive upgrade.
Oh, we wouldn't do that.
oh yeah, no, because you base the chips the memory is soldered to the GPU. So
Yeah. Well, I'm saying you'd have to do a GPU swap.
right. But for future systems, it may have an impact on how we use it. On the other hand, for the current system, it means that you want more bandwidth per GPU because you're going to be computing out of
In and out of memory so much.
Yeah, but so for example, with Sierra, we have 256 gigabytes of DDR4 memory in 8 DIMMs for the total node. And so you need to be able to pull that data into the GPUs at a fairly high rate. Otherwise, you're going to spend all your time moving data back and forth between memory, and it doesn't matter how fast the GPUs go.
It's just going to grind itself. Yeah.
It's an Amdahl's law thing, right?
Yes, it is.
Right.
Yeah.
So we chose that balance. And you know, as I was telling you earlier, we're getting enormous speed ups for many
Yeah,
packages.
you were saying that. What was that again? What were those numbers?
Let's say you just run your package on the CPU only. And then let's say you run it on the CPU and the GPUs in the way you just described. So our packages are running between 8 and 13 or 14x, depending, times faster than running just on the CPU alone.
That's incredible.
Yeah, so we're very pleased. We're still having problems with Monte Carlo. And 1 or 2 other packages are still, we're still in the single digits, you know, above 5. But we want to get up around 10 if we can. So we're pretty
way more than Moore's law.
Yeah. So we're extremely pleased, and I'll use another word: relieved. I mean, being in my job. Between being pleased and relieved, there's just a very small gap.
But so I mean that's the interesting thing is, as Michael mentioned, we had the choice between 2 GPUs and 3 GPUs, and we saw that our codes were getting a number of them were actually getting very good use of the GPU. So it was tempting to go to the 3 GPU system. But what we're actually seeing, for example, the benchmarks we used in the procurement are divided between 2 categories: throughput benchmarks and scalable science benchmarks. And the scalable science benchmarks are basically a single type of physics that you're going to try and run across the whole system at the largest problem size possible. Throughput, the idea is that to some extent you're going to run it on a smaller amount of system, but it also more represents the type of computing represented by our most significant applications, which we call the integrated codes. Right? And those are the ones that involve these multi-physics, multiple physics packages, and basically they have to cycle through.
It's a workflow.
Yeah.
Thing.
Well, so within a single time step, they're solving multiple types of physics.
Okay.
So they basically have to cycle through different data within a fairly short period of time. So no matter how large you scale them, that's kind of characteristic of how they work.
It's like a climate code.
Okay.
Right.
And
Lots of different inputs.
Yeah.
Okay.
And so as a result, that means that for us at least, the way we're going to use the system, it's very important to be able to make use of the full memory of the system. And what we see is that Sierra is getting over 6x improvement on those benchmarks, and that, as Michael kind of indicated, translates directly to the actual applications that we're running.
Yeah, 6x over
Sequoia.
Over Sequoia.
Okay.
It's a
Or
different-
Titan, which is the previous generation system at Oak Ridge. And in fact, the system at Oak Ridge Summit is getting less than 5% higher, despite being,
Bigger.
yes, a significantly larger system. It has the 3 GPUs, but also roughly a third. So we could have, if we had gone with
The third GPU.
the 3 GPUs, it would have still been about a third larger than Sierra. All right. So for our applications, there's no question that dollar for dollar, the system we ended up procuring is the better choice.
For us.
Yeah, for our workload.
Yeah.
In fact, because it's almost comparable to a system that would have been a third larger with 3 GPUs.
We had a little less money.
A little better performance per dollar, though.
Well,
Better price
yeah,
performance.
they may argue about that, but yeah, I think we did.
Well,
They're not
well.
here.
So when you look at the scalable science, they get a little bit better, not a whole lot better than a third more on the scalable science codes, which is more characteristic of their workload.
Okay.
So by scalable science, you're talking about one package or most 2 packages.
Running on the whole system.
Right. So for instance, molecular dynamics, you're just running MD all the way across the machine. Whereas with a climate code or with a nuclear weapons code or a code which models an engine, it's an entire physical system that you're trying to model. You have to have multiple physics packages. Each one models a different aspect, radiation transport,
Sure.
high explosives, I mean, you name it. There's lots of different pieces. Each one of those has to run well, and they have to be able to communicate with the other packages. That makes it much, much more complicated. And as a consequence, you have to rely much more on the CPU, both to manage the calculation and also do the parts that don't thread sufficiently well.
okay.
Because the CPU is much faster
Yes.
engine for
the
some kinds of
non-threaded
work.
things, for single
Yeah,
threaded.
yeah, it kind of saves you from death by Amdahl's law.
Yes. So let's talk about the future to the extent that we can. El Capitan.
Yeah.
So El Capitan will be the system that follows on to Sierra. It's part of the Coral 2 procurement. Sierra and Summit are systems from the first Coral procurement. It is, so that RFP and procurement will be buying the fielding the first exascale systems in the United States. So, I mean, during my time here, I've already seen 5 orders of magnitude improvement in computing capability. That'll take it to 6. I'm not sure quite. Yeah.
How many orders have you've seen?
Well,
You've seen everything from
I
teraflop
came in
on
the
Well, he's
mega flop.
before
I've been here
Terra.
40
Yeah,
years.
I started when we were
You
just.
start teraflop.
Yeah.
So I was, let's say I started out, things were around 10 to the 6th, 10 to the 5th or 10 to the 6th, and now we'll be at 10 to the 18th. So that's 12 orders of magnitude in 40 years.
It's a lot.
Yeah, yeah. Well,
It's kind of
I can
mind-boggling.
feel
It
it,
really is. My mind is boggled right now.
yeah.
If the camera could see me, they would see my mind boggling.
The
That's
thing
something.
that's most kind of distressing is that while the peaks have increased, we're still, the efficiency of the engines has stayed very low.
Yeah.
And that's been true pretty much from the beginning. It may be that the CPUs are more efficient, but it's always been in the single digits, generally speaking. And if we talk beyond El Capitan, you know, I mentioned that getting the next factor of 2 is going to be expensive. You know, at constant cost, $600 million, you might get a factor of 2 over 4 years or something if you don't change your programming models or don't do something. So I think it's time to be thinking about getting more out of your computers by either by changing the architecture or through clever software approaches. Now, machine learning is one.
I think
We've
that's-
mentioned,
yeah.
you know, we grasped that a few years ago. We're, you know, in fact, we've got some LDRD efforts at this laboratory that are fairly advanced that are looking at machine learning. One example is with these ALD meshes where the mesh moves around. These cells have vertices, and as they move around in the fluid, the vertices can cross over. So, you know, you have something like this, and then it looks like this. When that happens, the code dies. So if you can anticipate that happening, so what happens if the code dies? The code crashes, the designer comes in the next day, he has to go back to the previous drop file or the previous instantiation. He has to clean up the mesh and resubmit. So a whole day is down the toilet, right? So on the other hand, if you have machine learning and it's able to detect that the mesh is going to degenerate, then it can renormalize the mesh, do what's necessary to fix the
Lost all
problem
that
on the
work in
fly.
time. Yeah.
And then the code, you know, that has to be done judiciously because
Yes.
you have to conserve certain quantities, energy density, the rest of it has to be done smartly. But the time to solution can be sped up by an order of magnitude if you don't lose a whole day each time
Sure.
the code dies on you.
But it's not something that's going to show up in the top 500 list.
No,
But it's going
but
to show up on your efficiency.
yeah, we don't care, right?
No.
We want to get our mission done. I mean, that's why we went with 2 GPUs, not 3.
Yeah.
And why I think we need to put, I would say that almost immediately we should be investing in more efficient architectures. You know, trying to find ways to avoid the bottlenecks, the memory bottlenecks and whatnot, the indirect addressing, the rest of those things, finding ways around that can increase the efficiency of the machine, since just putting more transistors down,
Yeah.
the costs are going to go up, the power is going to go up, and
And we're not getting the improvements.
yeah.
Well, and there's also just a limit to it,
There
right? I
is.
mean, there's a physical limit to.
Right.
We're
How-
very near the shrink limit now.
Right, I
Yeah,
mean, so-
exactly.
I mean, there are chips shipping from Intel, I guess, that are 10 nanometer. Most are 12 or 14 these
Yeah.
days. But there is a fair amount of work going on in the fabs to do 7 nanometer, and we would probably expect to see 7 nanometer chips in El Capitan. Potentially, we could see 5 nanometer in El Capitan. But
Boy,
thing is now we're getting kind of near the end. I mean,
Yeah.
from what I've been told, it's if we can go beyond 5 nanometer, 3 nanometers probably the physical limit. At which point,
Yeah. I've had people tell me that like 7 is the physical limit because atoms are lumpy, and you're
Yeah.
getting into the point where you've got just a very
it's not
few
known.
atoms on the base.
I'm not the physicist to
No,
make the
no, I'm
judgment
not
on that, but you know, everybody that I know says there are definitely people they're actually in the laboratory, people making 5 nanometer chip.
Mm-hmm.
So it can be done. Whether you can mass produce them is a question.
the thing.
Can you
The
go
complex
below that
is-
to 3 nanometer? It may be that may be you can get to it in the lab. You can't get to it in
Mass production.
right in the
Yeah.
sort of thing that you can actually field a real large system with, or you can sell for phones and desktops and everything else.
If the yield is low, somebody has to absorb that cost.
Yes, yes.
But at that point, you know, we're down to, all right, if we're going with traditional architectures, even calling a GPU a traditional architecture, you know, you're now running into the limits in terms of how much smarter we can be about how we design them.
Yeah.
You know, a few percent improvement is a major deal at that point, and doubling just isn't going to happen. You know, so new and different designs, new and different technologies are really the only answer.
I think that's what we're looking for now soon is a leapfrog. Something that's going to be different. It's a change in programming.
It's gotta be
models,
a change,
in architecture. It's
It's going to have to be a pretty radical change, too.
Yeah. Yeah.
So, some vendors have ideas. I mean, for instance, the Intel approach is currently, it's non-von Neumann. It's very interesting. There's others, too, that are even more radical than that. I can't talk about.
Pretty
but-
radical idea myself of getting 64-bit precision. Run it twice at 32 and average the result.
Well, that's interesting that you should mention
Or
that.
4 times at 16.
We actually have a
Yeah.
project here being led by Jeff Hiddinger, who's the director of the Center for Applied Scientific Computing, which is the computer science, computational science, and applied mathematics research division here at the laboratory. And that project is specifically looking at something that I call, and I think Jeff might have been the first that I heard use this term, but it's the only way I can conceive of it. I think he has some other term now that is more descriptive in applied mathematics, but he called it adaptive precision refinement.
Wow.
So a fairly well-known technique for, an algorithmic technique for improving the way, you know, the accuracy with which you can simulate complex phenomenon is adaptive mesh refinement. So you have a large mesh over an area, and then where things are more complicated, you refine the mesh and have a finer grid mesh in those areas. So instead of doing adaptive mesh refinement, where you actually have error estimates and that drives how much you refine the mesh, he's looking at stacking different precisions.
So when I was just making a joke, which didn't work.
Yeah, because it was true. You didn't realize that your statement was actually highly accurate and that it actually
You
works.
guys would know that. Okay, you're working on that.
Yeah.
And he's getting very interesting results. We're very much anticipating that this sort of approach will become a hallmark of the more traditional aspects of our simulations. We're looking at ways to closely wed them to things like machine learning, so that you can go to longer length scales and longer time scales to simulate complex phenomenon, and then combine them with models at finer scales. All right, but to handle the more complex mathematics and to improve the performance we can get out of a system. So in Sierra, the GPUs can calculate single precision number arithmetic twice as fast as double precision
Yes.
arithmetic. And they then also have something called tensor ops, which take half precision arithmetic inputs, and then they can do multiplications in half precision and accumulates additions in single precision. They do those in 4x4 matrix multiplies, all right? So that those end up being multiplications and additions. And they can do those at effectively 16 times as fast as they can do double precision arithmetic. Now, the type of half precision numbers that those use are IEEE half precision, which means that you cut down the size of the exponent as well as the mantissa that's being represented. So the range of numbers you can represent is much smaller. From talking with Jeff, that makes it very hard to apply those numbers to the types of applications we care about. There are proposals actually to use different number representations at half precision, which keep the exponent the same, and so the range of numbers.
The range that you need.
Right. You just have less precision, but because we can stack them up, we're actually very hopeful that we'll be able to use even down to half precision numbers.
Very cool.
Yeah.
This has been a fascinating conversation, but you guys are talking me out of battery.
All right.
So we're going to close this off.
Yeah, you're only going to keep 2% of this anyway.
No, I'm going to keep probably 95% of it, depending on the exponent and the mantissa. But this has been just great. Thank both of you for your time.
Oh, you're welcome.
And the tour and all of that. And next time I'm through, I will swing back by
Sure.
and get some more education. Thank you again.